Thank you. So this lecture is going to have almost nothing to do with the first lecture. And in the third lecture, I'm going to combine the two. But just so you, if you're worried about having gotten to the limit of your understanding with the last lecture, it doesn't matter. So the first thing I'm going to do is I'm going to fix a base. And I'm not going to worry about what's going on with more general constructions because I don't want to do a technical talk. I want to do a basic talk. So fact, which I'll explain later. So I'm going to talk about the Zariski topology, and what I say is going to apply to the Nisnevich topology, but I don't really need the Nisnevich topology for the statements. I just need the Nisnevich topology for the proofs. So I'm going to sort of slide that under the rug. So that's that. So the sheaf, Z parentheses I. So it's some chain complex. And so what is this? This is a Zariski sheaf. So that means it's functorial in X. So if I map X to Y, I get a map from the sheaf on Y to the sheaf on X, as long as everything is smooth.
What is N here?
I can't use K, right? Because K is on my field. I can't use N because you're complaining. So what letter can I use? Rho. I don't care. It's just an index. So there are these sheaves. And the Motivic cohomology, Hn of X, there's one of these things for all I equals 0, 1, 2, 3, etc. I don't understand what you mean that they're all the same. I'm trying to use I for the twist uniformly through this talk, yes. Depends on I, depends on I, depends on I, depends on I. It's a chain complex of sheaves. So let's make it rho comma I, rho plus 1 comma I minus 1 comma I, and I comma I. I didn't really think that that would be an issue that you needed to worry about the subscripts. But anyway, for every I you get a chain complex, and the chain complex uses different C's. Point is that this is the Zariski hypercohomology of X with coefficients in this chain of sheaves. So now you know the definition of Motivic cohomology. We can all go home. Here's an alternative definition, which is called Bloch's higher child groups. And that is Hn of X, coefficients in Zi, is isomorphic to chow, I of X, coefficients in 2I minus N. And I need to define that. Well, I don't want to define it very carefully because that would take about a half an hour. But you get chain complexes. And this is where my notation runs me into trouble. So I wrote out the notation for the chain complexes. So instead of talking about chain complexes, I want to talk about a simplicial abelian group. Zn of x cross I dot. So I'm going to put a little tilde on there. So Zn of x cross delta dot. So these are codimension n cycles. In x cross delta p, which meet all faces properly. And the condition for that they meet all faces properly is that this gives you a simplicial set. And now we have definition of the chow I of x comma n is that it's pi n it's pi I of z tilde n of x cross delta dot. So the fact that these are the same is not necessarily an easy theorem, but it's not particularly crazy, and I don't really care about it. But the point of the matter is that chow n, this is all designed so that chow I is x0 is the usual chow group. Which is usually called chow I of x. Now if I translate chow I is equal to chow x0, then I take chow x0 and I translate it over to this, what I get is that h2i x comma zi is isomorphic to chow I. So the connection with higher chow groups is that this is something which has to do with a very classical notion, namely the chow groups. And also, at the other extreme, z of 0 is a constant sheaf, z in degree 0. So hn, hi, hn of x comma z0 is hn of x comma z, the usual Zariski cohomology, and that's equal to z if x is connected. So here we have two different extreme ideas of what this is. So let's see, I want to do this. So also, if I equals to 1, z of 1 is homotopic to the sheaf, the complex of sheaves, which is OX star. This is in degree 1. So the H1 of x with coefficients in z1 is the same thing as OX star, the units. H2 of x with coefficients in z1 is the Picard group, because that's the first cohomology, Zariski cohomology with coefficients in OX star. And Hn of x with coefficients in z1 is equal to 0 for other n. So we understand what z0 is, we understand what z of 1 is. We really don't understand any of the other z's except for the connection with Chow groups. The last what? This is given by the fact that OX star has a, so if F is field of fractions of x, there's a resolution like this, where these are Flask. And so if you want to take the cohomology of this, you just take the global sections of this and the global sections of this. So here's a complex concentrated in degrees 0 and 1, and then there's nothing else. Okay, so what I'm basically trying to do here is to tell you that these are important complexes, that they have lots of good properties, and we don't really want to worry too much about what their actual construction is. So the next thing is, here's a theorem, and that is that there's Kn of x tensor q. That's the direct sum of groups Kn of x of k. So these are q vector spaces, and where Kn, parentheses I, of x is isomorphic to h 2I minus n of x with coefficients in zi. Whoops, qi. So there's a connection with K-theory. And I should point out that if I take h star of x with coefficients in z parentheses I, and I tensor with q, that's the same thing as h of x with coefficients in qi. So the q here doesn't really do anything except for kill torsion. And this is reminiscent of Grothendieck's Riemann-Roch, which, among other things, says that K0 of x tensor with q is isomorphic to the direct sum of the Chow I groups of x tensor with q. So if I take all of this stuff and I read n equals to 0, this is more or less what I get. And the connection with the Chow I of x, the 0 is given by this property. Now we can also go mod L. So L is some number like 17 or 24 You have this sequence. I didn't say this, but the individual components of these things are these CEIJs are free abelian groups. So this is a resolution. So what it gives you is a long exact sequence with hn plus n minus 1 of x coefficients in z mod li to hn of x with coefficients in zi multiplication by L to hn of x with coefficients in zi to hn of x coefficients in z mod li. Here's the boundary map and so on. And I can break this up into hn of x with coefficients in zi mod L to hn of x coefficients in z mod L parentheses I and then the hn plus 1 of x with coefficients in zi. So I'm taking the L torsion subgroup with that and I get to 0. So this is like a universal coefficient theorem. So I can take Motivic cohomology with coefficients which are finite. And why would I do that? Well, there's this huge theorem. So it's due to Voivodsky et al. So by et al. I mean you include Suslin, you include Deline, you include Bloch, you include Kato, you include Bailenson, you include me, you include, I'm probably about 3 other people. Rost. Marcus Rost. I thought I said him. Didn't I say him at the beginning? So the theorem says if F is a field, and since I'm working in schemes over a field K, it could be K, but it could be any other transcendental extension field of that. Then the Motivic cohomology of X, of F with respect to Z mod L, parentheses I. So when I write F, I just mean the spec of F, but spec gets in the way there. There's a norm residue map, which takes to the Étale cohomology of F with coefficients in mu L tensor I. And that's an isomorphism. And so now I need a technical assumption, and that is that the characteristic does not divide L, which is the same thing as saying that L is a unit, or it's the same thing as saying that L is a unit of F. So if you know anything about Motivic cohomology, if you know anything about Étale cohomology, then you can say something about Motivic cohomology. So more generally, if pi is the map from the Étale site to the Nisnevich site, then you can take mu L tensor I, and you can take R pi lower star. So what is R pi lower star? It's the right derived functors of the push forward, but what it really means is You take an injective resolution in smooth sheaves over K, which means that the individual sheaves that you choose are injective objects in this category. And then you take the push forward and you get a chain complex of Nisnevich sheaves, and that's what this is. Well, that's not really what I want. So this is the truncation. So tau less than or equal to I of a chain complex is the chain complex which goes Ci minus 1 to Ci to the d of Ci to 0. So this is a good truncation. So these mod L complexes, the Z mod L I, are actually coming up from this construction, and this statement right here is equivalent to this statement right up here, although that's not obvious. This formulation of the statement is due to Bloch and Kato, and implicitly in Milner. If you read Milner's original 1970 paper with your eyes squinted, you could say that he really said that this should be an isomorphism. And this is due to Bailenson, and with a small variation due to Lichtenbaum. And so this is true, and this is true, and a consequence of this is that if the dimension of X is D, then Hn of X with coefficients in Z mod I to H étal of X with coefficients in mu L tensor I is an isomorphism. If n is less than or equal to I. So as an example, what?
There's no D in this case. You make an assumption about
Yes, depends on the definition. And less than or equal to I. So if you want to understand the Motivic cohomology over a field X, then you have to understand the étal cohomology, and it gives you the Motivic cohomology in a range. So if you sort of plot, here's n and here's I, and here's n equals I. And this is the good zone. Okay. So what else can I say about this? There's a vanishing conjecture. Which is still wide open. And the first thing is that Hn of X with coefficients in I is equal to 0 if n equals 0, minus 1, minus 2, and so on. So the if you use this,
could you please move the black bottle that it not overlap the text? The left.
sorry, my My ability to judge angles is a little bit off because I have a steeper angle than you do. Okay, so if you take this and or even this, and you take n negative, then the negative cohomology, atal cohomology, is 0. So this tells you that you already have 0 vanishing with mod L coefficients. And so what you end up with is these groups are uniquely divisible. And possibly L torsion in characteristic of K equals L, well, divides L. So whatever these groups are, they're uniquely divisible, and a uniquely divisible abelian group is a rational vector space. So I'm going to call that UD for uniquely divisible.
What's the assumption about I here, about this symbol? Because when n is 0 and I is 0, that's
Yes, and that is except for h0 of x with coefficients of 0, 0. Which I'm going to just assume x is connected so that I can just say z. Right, so that's the first part of this. And the second part of it is K I n of x is equal to 0 if I is less than or equal to n over 2, except for, of course, K0 parentheses I of x. Which is equal to z if I is equal to 0 and 0 else. So if I worry about K0, there's a little bit of a squeeze. Now I want to point out that this conjecture is due to Soulé and it's due to Bailenson. And there's a slight difference in the way that they formulated these conjectures, and the slight difference is what happens when you're in this case or in this case. So if we worry about I equals n over 2, then Bailenson gives you nothing, but Soulé gives you something. And so I talked with Bailenson and Soulé, and they said that basically this should be the version of the conjecture. Okay, now I think I've gone on long enough without giving you any definitions. So in order to do this, I have to sort of proceed by inventing categories. So well, let me say core xy is a free abelian group on the irreducible W contained in x cross y, so that the projection from W down to x is finite onto a component of x. So normally when we think about this, we just say, let's just assume that x is connected, in which case the thing I put in parentheses doesn't matter at all. But if you have an x which has got several different components, I just worry about that. So here's a picture. So I hope I can do this correctly. So this is an example of a W. And if I pick an x here, then I get a bunch of points. And so this is a finite correspondence. So generically, the map F, so I'm just going to call this F. F from cycles on X to cycles on Y takes the class of X and it maps it to the sum of the classes of the yi's. I say generically because I'm assuming that everything is in general position in order to make this definition. If things are not in general position, what you have to use is the push forward. And I don't really want to talk about the push forward of cycles, but if you take a cycle here, you pull it back to a cycle on W. Well, you can't really pull it back to a cycle on W unless W is smooth. But let's assume that W is smooth. Then you can pull it back to a cycle on W, and then you push it forward to a cycle on Y. So the idea is you start off with X, you go up to W, and then you go over to Y. If W is singular, you have to play some games. Okay. Wait a second. Okay. So this is a category, and I didn't do this right. But for the push forward from W to proper over Y, being finite implies being proper, right? A finite map is always proper. This is finite. I'm not saying anything about this map. This is just some map. So correspondence from so if I take Y to be a point, it's going to be arbitrary. So if I take a correspondence from A1 to a point, then anything which is finite over A1 is going to be a finite union of spec of fields. And if I take a finite union of spec of fields finite over K, and I map it to A1, that's definitely not going to be a finite map. So we can compose correspondences using push forward. So if I have a So if I have a cycle from X to Y and I have a cycle from Y to Z, then I can take the intersection of these, I can take this cycle and pull it back. I take this cycle and pull it back. So if I take a cycle over X cross Y and a cycle over Y cross Z, I can take this cycle and I can pull it back to a cycle over X cross Y cross Z. And I can take this cycle and pull it back to a cycle over X cross Y cross Z. Then I have two cycles in the product. I can take the intersection, I get a cycle on X cross Y cross Z, and then I push forward to a cycle on X cross Z. So this gets a category. Now the advantage of this particular category is this is an abelian category. Whoops. It's an additive category. Because what I've decided is that the morphisms are free abelian groups. And since the morphisms are free abelian groups, then a map from one thing to another is in a free abelian group. And that's enough to give you the structure of an additive category. So now, once I have something like that, I can proceed to do something like an abelian version, a homological algebra version of what Vesna did just an hour ago. And so that means that I can talk pre-sheaves with transfers. And that's the same thing as pre-sheaves of abelian groups on the category of correspondences. So an example of that would be if X is smooth over K, well, is a variety over K. Then I can take correspondences from blank into X. And that is something that's going to take a Y to correspondences between Y and X. Now I realize that I've just reversed the order of X and Y, but I hope that's not a problem. And so this is a pre-sheaf with transfers. Now we can look at chain complexes. Oh yeah, so here's a remark. The associated sheaf of a pre-sheaf with transfers is also a pre-sheaf with transfers if F is A1 invariant. And so I want to remind you that that means that F of X is the same thing as F of X cross A1 for all X in smooth K. Now I have a problem with the boards. I have to be careful not to block off your vision. Okay. So we start off with a field and attached to every smooth variety X over this. We get an abelian group from these pre-sheaves with transfers. And this also makes sense oh, I didn't give this a name, and I should have. So Z transfers of X is going to be that particular pre-sheaf. Now, this also makes sense if X is singular. Or if X has a base point. Then you sort of take Z transfers of X modulo Z transfers of a point. You can call that Z transfers of X comma the point.
When you talk about the associated sheaf, which topology do you refer to?
So I could be doing any one of a number of topologies, but what's going to happen is that I'm going to be thinking that I'm in the Zariski topology, and secretly it's in the Nisnevich topology. But when I start taking hypercohomology and things like that, it isn't going to make any difference which topology I have. This is Zariski or Nisnevich.
But I mean, if the morphisms are correspondences, there's nothing like it.
So when I say finite correspondence, I mean a finite map in the Zariski topology.
Okay.
You only need the Nisnevich topology as a technical device for proving theorems, really. The main theorem is that the...
But now, when is the correspondence in Zariski cover, for example?
When are they what?
When is the correspondence in Zariski cover, for example? I mean,
When is it Zariski what?
at Zariski cover or whatever topology. I mean, the morphisms in this category are not morphisms for schemes, but correspondences, aren't they?
Morphisms are correspondences, and so I don't have... okay, so... So I think that this will address your question. We can talk about the category of Nisnevich sheaves with transfers. And so that, with correspondences, and that with transfers. T has to correspond to this T. So the first thing that they have to be is a pre-sheaf with transfers. And then the second thing is that they have to be a sheaf in the Nisnevich topology. And here's a remark. If F is homotopy invariant, A1 invariant, this is the same as being a Zariski sheaf. This condition.
Now, the second condition sheaf in this Nisnevich topology means that
I forget all of the business about correspondences as a sheaf. On smooth over K. Okay? Okay, so now GM is appointed variety. And we just pointed out that it makes sense if the thing has a base point. So that means that Z transfers of A1 minus 0 is the same thing as Z transfers of a point plus Z transfers of GM. And so the definition that we can use is that Z of 1 is G of M transferred one time. So in other words, it's the complex which is GM in degree 1 and nowhere else.
So you're really in something different over there, right? Because A1 minus a point is G.
Ah, I'm being very tricky. My notation GM refers to a pointed variety. My notation A1 minus 0 refers to a variety without a base point. Because it has a base point, Z transfers of a point is a direct summand of it. And so I'm using Z transfers of GM to be the complementary. And thank you for reminding me to put that in there. So with this definition, you see that I'm going to get the cohomology of GM transferred several times, and I think I wrote that up there at the top, right? So if you just take this definition and you take the cohomology, you get that. Now here's the definition in general. So you can just do that. Well, maybe I didn't unpack this enough. So you take so you take the tensor product of all of these. In other words, what you get is that z parentheses n is isomorphic to z parentheses 1 tensor with itself n times. Okay, so now where are we? I've given you some crazy definition of this category of correspondences and this definition of a presheaf with transfers. And I've given you an example of something here. And following the example of Vesna, I'm going to say this is an abusive topology of terminology because I'm really not saying that the Z transfers is A1 invariant. What I'm really saying is you have to play this little game of A1 invariance. And here's what that trick is. If F is a presheaf with transfers, so presheaf with transfers is one of these things. C star of F means F is the function which takes x to F of x cross delta dot. So it has a chain complex. So in other words, this is F of x F of x cross del 1, F of x cross del 2. So this is the usual game that if you take a simplicial object, so del dot is a del n is spec of k adjoin x 0 through xn, brought out by the equation that the sum of the xi equals to 1. So this is a variety that if you realize it over the real numbers, you get an n simplex extended linearly to the plane. And these fit together to form a simplicial scheme, a cosimplicial scheme. If I apply a contravariant functor to it, I get a simplicial abelian group. And then I take the simplicial abelian group and I convert it to a chain complex by doing this game. And now I take C star and I just define this to be this. And the fact is that F is equivalent to C star of F. And C star of F is homotopy invariant, A1 invariant.
Equivalent where? So F is equivalent to F in which?
So this is a category of chain complexes of sheaves. Yeah. So where am I? I started off by saying Z by is a chain complex like this. If you look at my definition here, this is a chain complex concentrated in degree 1. This is a chain complex concentrated in degree 1. But when you take a resolution of it, it becomes a chain complex which stops in degree 1 and is 0 in degrees greater than 1. So that when I take the tensor product of n of these things, then I live in exactly this territory. So theCij's that I have up there are the individual terms of this complex right here. Okay, now, here's a theorem. F is algebraically closed, that the Kn of F is isomorphic to H0 of F, coefficients in Zn. And so this is Q mod Z plus uniquely divisible, or Z. So this is n equals to 0. This is n odd. And this is n even, n greater or equal to 0. So this gives you some sort of an idea of what is the connection between K-theory and Motivic cohomology. And I think I'm out of time, pretty much. So let me just stop there. Didn't get to use your bell.
You keep on the right.
Okay.
Questions?
Yeah.
Can I ask you, if X is singular, are this kind of the right cohomology for singular schemes?
So I didn't talk about what you do for singular schemes.
You said you can define them.
I said you can define it. So, so there's a new topology which I didn't introduce called the CDH topology, and the CD stands for completely decomposed, which was invented by Voevodsky, so it's due to Voevodsky, and the H is it's due to Nisnevich. Sorry, it's the H topology that was in Voevodsky's thesis that's due to Voevodsky. So my joke is that CDH corresponds to Nisnevich and Voevodsky. Okay, so you take the CDH topology and then you run the whole game through in the CDH topology, and that's what gives you some theory for singular schemes. It doesn't change what you do for smooth schemes, and it has the property that the connection is no longer with K-theory, but it's with the homotopy K-theory.
But if one just does this zr of X for a singular X, and that kind
This makes perfectly good sense if you just read the definition, because the definition didn't have anything to do with X being smooth. And so the definition goes through.
so one doesn't mean CH to be the right.
No.
It won't be the right.
Well, it won't be the quote right thing because we're in the wrong topology. Yeah.
When we went from simple Schrodinger's to chain complex, how did we do that?
So there's a game. And this is called the Dold-Kahn correspondence. And that is that the category of simplicial objects in A, so this is some nice object, an exact category, is in one-to-one correspondence with chain complexes in A, which are 0, so C0, Cn is equal to 0 if n is negative. And roughly speaking, what happens is that if you take a simplicial object, I don't know, let's say k dot, then what you're going to get is k0, k1, k2, whoops, 0, k0, k1, k2, etc. And this is the alternating sum, where you take the sum of the -1 to the I of the del i's. So if you take a simplicial object and you play this game, you get a chain complex. And I'm cheating a little bit because one has to reduce it, but that basically gives you a equivalence of categories. And so if I take any simplicial object, I can think of it as a chain complex, which is 0 and negative degrees. And that's the game I was playing. And if you want to know more about this, then I wrote a book on homological algebra, and you can look there. Any other questions?
I would like to ask whether here you associate about a finite map and sum. Is it possible to generalize because here your coefficients are always 1. You have
Well, the coefficients are 1 because I said generically. So what you really have to do is you have to take the push forward, and the push forward takes into consideration the degree of the field extension that's involved and with the amount of nilpotence that's involved. So I'm giving you the generic idea because this is supposed to be an introductory lecture, and I give you an introductory idea of what a correspondence is. So the picture where you take the sum of the yi, that's what works generically, but it doesn't work uniformly because you have to worry about finite field extensions and whatnot.
But is it possible to take a twisted? It look like some kind of orientation. Twisted. I don't know, but just like you have an orientation and you sum up to some -1, etc. Is it possible?
So if you're familiar with Grothendieck's work on Chow motives, in Grothendieck's work on Chow motives, you're allowed to use minus signs, but the difference is that Chow motives are not always finite over x. If you restrict yourself to motives which are finite over x, then you only have plus signs.
I'm asking more than a sign.
Maybe we should talk about this later because I think that this is a specialized question.
Maybe then if only mark them, maybe the confusing thing is this is really only a definition of the level of generator. There's no child groups involved. There's also the math.
That's right.
Anything because we don't talk about child groups.
The Chow groups are obtained by taking the cycles modulo and equivalence relation, rational equivalence, right? And I'm not using rational equivalence for this. Rational equivalence is something that comes out later.